This is the second part of the second lecture series on statistics for PS328. We're now going to move on from looking at tests for statistical independence where we were not dealing with, in essence, two interval level or continuous variables, and look on to methods that deal more explicitly where we have our dependent variable in particular, but also the other variables are going to be more likely to be interval level or ratio level. And in particular, I'm going to introduce you to three concepts, which is covariation, the equivalent of understanding sort of, it's a notion that's very closely related to independence, correlation, and regression. So again, when we looked earlier, we saw this idea of statistical independence, where you were looking at the probability of one variable depending on the probability of the other, or the values in one variable depending on the value of another variable. So this is, for example, what independence looks like, right? Where the chances of it raining are equal depending on whether it's cloudy or sunny, which of course happens in England, not so much in Amherst. Now, the tricky part that we need to do is we need to start thinking about how we have the same type of concept when what we're dealing with are much more or less continuous variables. So we look at something that looks more like this, where what we're really interested in is sort of, does the value of y depend in some way on the value of x? And the equation that we tend to use to sort of start off with the very most basic idea of getting at this conditional dependence is covariation. So in essence, what we will do is we look at, for a single given point, we look at the difference, so sort of how far that point deviates from the mean along the x-axis, and also how far that point deviates from the y-axis. And to calculate the covariance between these two things, we times those two together and then sum them. And so this is very similar to the idea of variance that we got introduced to earlier, but now we're looking at covariance. Now we still need to do a test with this, but this is the first thing that we sort of calculate, as it were, which is basically whenever x goes up, is y going up or down? And of course, you can imagine that if it goes up sometimes, down sometimes, there's not going to be a relationship. Those two things are going to be independent. But if it's consistently either whenever y goes up, x goes up, or whenever x goes up, y goes up, or whenever x goes up, y goes down, then you're going to have either positive or negative covariance, i.e. that will start to look more like what we think of in the sort of more simplistic case from the earlier diagram as some form of conditional dependence. So one of the statistics that we use to look at this type of covariance is the correlation coefficient, which basically is where we look at the covariance in x and y, and we divide it by the two variance of x times the variance of y. Again, a more advanced class will walk you through why it works this way. If you sort of look at it, you can probably tell that basically why it is that we calculate it the way that we do. And in essence, it gives us a number. It gives us a number that should, in theory, vary between -1 and +1. The reason that it's got to vary between that is because, of course, the covariance on the top itself could be either negative or positive, right? For the reasons we went through on the previous slide where we said whenever x goes up, either y can go up or down. It can only be negative or positive. The variances, of course, by definition, have to vary between 0 and 1. They're constrained for that way. And the variances themselves are constrained to being positive. And in addition, if you think about what the numbers are, the variance of x times the variance of y can never be smaller than the covariance of x and y, simply because of the way that it's calculated. So in other words, the most you could have is them being exactly equal. Thus, that's why the overall R is going to range between -1 and +1. Now, in terms of, again, looking at software, so here's the Stata and the R commands for this, some of which we went over, I think, last week in class, and we'll go over again whenever we do the in-class labs. But what you get is something that looks like a correlation matrix like this. You can make them weighted or unweighted. In this case, this is a Stata output that I think does have them weighted, or maybe it's SPSS, I'm not sure. But what you get are numbers. Basically, if you look at this MR great by DV crate, you can see that that correlation is 0.58. And again, median age, I guess maybe, for MR great or MRG rate, I'm not sure. Again, you see that that's a negative. So in essence, this is what you get. You get some number, but that doesn't tell you actually much how to interpret it. So the first thing we want to think about is how do we interpret just positive versus negative correlations? So graph A shows a strong positive correlation. Graph B shows a strong negative correlation. These are correlations of essentially about a 1, right? Where there's almost a perfect correlation. There's almost a perfect line you can see there with not a lot of spread between it. When you get to more moderate, you can see both on the graph C and D, things spread out a tiny bit. So that's a positive 0.75 on the top and a negative 0.6 on the bottom. So you can see again that means the way we would interpret this is there's a pretty tight correlation, and in addition, as the x variable along the bottom goes up, the y variable goes up. That's the top graph, A and C. And in B and D, it means as x goes up, y goes down. So another thing to check out here is that E basically means no correlation. This is a case where as x goes up, y is just as likely to go up as it is to go down. And also a curvilinear relationship. And it's one of the reasons that we'll come back to this again in future lectures, but it's really important to often plot and not just look at correlation statistics. You actually want to look at the scatter plot, is because sometimes if you tell the computer find a correlation, it will tell you there's a nice straight line between x and y. But if we look at graph F, what we can see is that it's not a nice straight line. It actually goes down and then it goes up. So in fact, we need a different type of relationship, some sort of a quadratic or a logarithmic, something that in some way deals with our curve. And we can do that by transforming either our x or y variable fairly easily, and then we can retransform it to a linear relationship. Again, we'll deal with that more in our third lecture series, but I want to highlight it even now, that when you look at your plots, you can often find deviations from linearity. So still, just to give you a slightly better idea, because I think that translating the magnitude of the correlation coefficient is always a bit tough. So again, the first plot is a correlation of 0. It's essentially random. Now you can see that it's actually pretty difficult to see a negative correlation. In this case, it's a negative of 0.03, but regardless, a correlation coefficient of 0.3 is actually pretty difficult to see. But I've actually told you before that that's about as high as it tends to get. In most cases, particularly between two variables that are measuring different constructs, you don't see much higher than that in individual level survey data. In particular, you'll see higher in aggregate level, country level data, or organizational level data, but not as much with individual level data. So you can see that even if you plot it, you might not think there's much of a relationship if it's got a correlation. By the time you get to 0.5, which is the third graph, you're seeing it much more clearly. And obviously, as you get above 0.5, all the way up to 0.99, things are getting nice and tight. And there, it's much easier to see the correlation. But again, keep in mind that one misleading aspect of scatter plotting is even if that negative 0.3 in the second graph is in fact a sort of significant correlation between the two things, in the scatter plot, it's really sometimes a bit difficult to distinguish from 0 when you're at these lower end of the correlation scale. So here are software commands for scatter plots. So the top is for Stata. For R, you can basically plot X and Y, and you can, I give a few options there for basically putting in a title and the X-axis label and the Y-axis label. One thing to keep in mind is that basically graphic commands have tons of options because you're often having to fiddle around to get your graphic just right. As we've talked about before, make sure you're saving everything in a syntax file. There's also a fantastic website called the R Graphics Gallery to work with. If you're sort of working around with your graphs and you want to play around with them some, you can also use the help, and it'll give you a list of graphic options, and in particular, it'll take you a command called par, which is sort of for parameters for graphics. Also very, very useful. And just asking people, how did you get that graph to look like that? One of the nice things about the R Graphics Gallery is it actually gives you example code to recreate the graph that you see there on your screen. So, but the simplest level as you're working on your homework is just to do a plot X, Y, and if you want to fiddle around with the title and the axis labels. But this way you can actually see pretty simply a scatter plot. So here is an example of a scatter plot. So this is a scatter plot of the number of runs that, I think this is from, sometime in the 1990s. This is Major League Baseball data for all the players. This is all the players who had some sort of a contract in the MLB and sometime in the 1990s. And you can see the number of runs that they hit that year is across the x-axis, and the salary they got in this case it's in the hundreds of thousands. So because people are often basically making $1 million and up over the year, you don't want to have your whole table stretched out that much. It can look funny. So sometimes you have to like make variables smaller. Or in some cases, actually, we'll see. In fact, you can also do things like take up the log of the number, because one of the things that you might see, and we'll come back to in this, is that it's actually not perfectly linear because you have this weird cluster down at the bottom. But at the very least, we can see here again, what we're doing in a scatter plot is we're taking x, which is the number of runs, by y, which is the salary, and we're plotting them. Now, having looked at that graph here, you might start to think, oh, that we might be interested in drawing a line through those numbers. So I'm going to have a second, look at the answers here, and see if you can remember the equation for a line. So hopefully you've remembered that the most standard equation for a line is going to look something like number 3. So y equals ax plus b, or maybe it's mx plus c. Again, there's different sort of standard notations, but the idea is that there's some x variable, there's some constant, which in this case is the b, sometimes is the c, and there's some slope that links x to y, and that's our slope a. So again, what we might be interested in doing is basically estimating. In this case, we might be interested in what's the relationship between the number of runs you hit and the salary, and you can draw a nice line. And what does that then tell us? Is it might tell us that, as you know, there's, again, if you remember anything about the slope of a line, you remember that it's the change in the change in y over the change in x. And so it can tell you, as you get 20 more runs, how much is the salary likely to increase on average, would be the way we might interpret a line like this. So wouldn't it be great if we had a way to actually estimate this line in a standard way that we sort of think that we're, in essence, drawing what's called the best fit line. So I know that like when my children were younger, they just had to draw by eyeball what they think is the best fit line. But wouldn't it be nice if we didn't have to eyeball it, but instead we had a nice standard way to all agree on what the best fit line was? And thankfully, statisticians have spent a lot of time on this and have come up with different regression techniques. In this case, we're going to be looking first at the idea of ordinary least squares. Again, I'm not going to give you a ton of background on it. I will have a slightly more advanced segment of the lecture that you can watch if you want to. That gives you some background on how OLS and how that line gets estimated. But for now, I'm just going to ask you to bear with me and work on interpretation instead of how these estimates get derived. But what's important then is that this regression, this line that I just drew would be called the regression line, is going to be the study of relationships between these variables. In this case, we're looking at the bivariate, i.e. between two variables, x and y. Next week, we will be looking at whenever you have multiple variables on the right-hand side. Regression provides basically a framework for testing the models of relationships, so we can posit different models and see whether or not they're more or less reasonable. And generally what we're doing is we're assessing the extent to which this outcome variable of interest, this y, is changing dependent on the variables. This x. In other words, what we're trying to do is estimate this regression line, which is, again, our standard y equals ax plus b. Plus, of course, because this is an estimate, this isn't 2 points makes a line. We've got a lot of points and we're sort of trying to find the best fit line. We've always got some noise that's getting added onto it. So again, we're looking at this relationship between the change in x and the change in y. Now, that all sounds really simple. And then if I show you this, you might start to go, oh, but I'm going to walk you through what the basic mathematical notation then looks like for our simple bivariate linear model that we're going to estimate using OLS. So the first is we can see the dependent variable, which is y. The intercept, so this is our constant in our sort of standard, mx plus b type of format, is just going to be our beta 0. It'll be our intercept. There's a coefficient or a slope. So this is, again, our change in y over change in x. Our independent variable is going to be our x, and then we've got some error term. And you can see that the reason we always have them denoted by I is because we've got many different cases. So we've got each data point is numbered from sort of 1 to n, where n is the number of rows in our data set or the number of cases in our data set. So again, when we come back to the graphical interpretation of this, what we can see is that these EIs are basically the distance between our line and each individual ith data point, right? And our beta 0 is going to be this point where basically the x equals 0, we're looking for where it intercepts the y axis, right? Remember that back in the day when you learned about lines. Our beta 1 is, again, our sort of change in y over change in x, our standard slope formula. And that's what we're going to be interpreting, right? So this is the setup we're going to be interpreting. So what we can then see is that now we're going to put hats on things. The reason we're putting hats on them is because now we're estimating it, right? So we assume, just like everything, whenever we were working with earlier statistics, that before that there was something out there in the population. We've now got a sample. We're going to try to estimate what our population looks like. So now our intercept of the value of yi when xi is 0, same as we saw before. Our beta hat 1 is going to be the average or expected change in y for every 1 unit change in x. So you'll see that just because that is the mathematical interpretation, but that doesn't mean it's always how you should present it to your readers, which we will come back to. So if we see our regression results, and these are actual regression results from the NES data set that we were using in our last homework, what you can see is it gives us an estimate for our intercept. It tells us also whether or not that estimate is significantly different from 0. That's our, if you go all the way over to the 4th column, you can see our t-value. You can also see that there's, our t-value and then the probability of t, which is our p-value, and that's very significant. You can also see in this case, what I've done is I've estimated whether or not the number of children that a respondent has an impact on their party identification. I think I didn't leave in that that's what's happening here, but we're basically estimating the impact of number of children on party identification. There's a negative impact, which means the more children you have, the more Democratic you are, because lower numbers on party ID are Democrat, higher numbers are Republican. So in essence, for every additional child, you go down 0.04 on the scale, which sort of means all 4% of the people who have, for each additional child, 4% of those people change one category on party ID. So not everyone is being affected, but some people are being affected by having additional children. And we can also see that it's very unlikely that the true number there is that there's no relationship. So that's our p-value of 0.005 means that there's only half of a percentage point chance. So it's 99, yeah. So half of basically we're 99.5% certain sort of that this number was not necessarily generated if these two things would be 0. So 99.5% of the time it couldn't be generated. 0.5% of the time our estimate could be generated even if the true number is 0. Again, you can go on and look at things like R-squared and observations. We'll be doing that more as we actually work through our homeworks. But what's really important here is to be able to look at the estimates and our p-values, because those are going to be the most important things that we're going to be interpreting as we go through our regression results. So again, here's a table that we might look at. This is pretty standard one that you'll see in any academic article. You'll often see, and sometimes people will not even bother to report standard error of the t. What they'll tend to just do is often use stars. But in this case, we've got intercepts and runs. You can see here that the intercept of negative 34.29 tells us something. We also see the runs. Interestingly, the intercept we can see from our p-value is not significantly different than 0. So it could just be the true intercept is 0, even though we got a slight negative number. The relationship, though, between runs and salary is clearly significant. Our t is 15.3, which means it's like 15.3 standard errors away from 0. And our p-value is very, very low. So this is how we're estimating things. What that means is that our y, basically if you want to know what line is being graphed there, it's the line y equals negative 34 plus 27.47 times x, where x is varying between 0 and 140 or so right here. Then if we want to interpret this more precisely, we might say players with no runs don't get paid. Again, that's not really the case because it's in essence, remember that negative 34 is indistinguishable from 0. We know that's not really the case because there's actually a salary minimum. And what you have is somewhat of a truncated distribution. Again, we'll come back to this next week because it turns out there do need to be some transformations because this is not a perfectly linear relationship. But let's just ignore that for now. What's really important is that you can see that each additional run translates into an additional $27,470 in salary per year. Now, two caveats to that. One is that this particular way, just saying each additional run translates into $27,470 doesn't really tell us much. Suppose everyone there varied between, they either got, it was like soccer goals. They got between 2 and 6 per year. So in other words, moving from the minimum to the maximum, or 0 to 6 per year, moving from the minimum to maximum only gets you an extra, say, 120,000. Now suppose it moves between 0 and 100 per year. All of a sudden you're talking about, almost 3 million. And so actually getting some sense of the range of the variables and what it say might mean between, in this case, if you look at my translation, if you go from being an average player to being at the 80th percentile, so an above average number of runs, that can mean $1 million a year to move from average to the 80th percentile. So from 50th percentile to the 80th percentile. Or you could say, I want to know what it means to move from the 20th percentile to the 50th percentile. Again, that should also be about $1 million per year, right? Because it's going to be the same number of categories. The other, of course, caveat here is that if you think about my actual data, the salaries are set based on prior year production, not on current year production, right? So they can't change the salaries based on the productivity. So in fact, what we're doing is we're assuming that like the runs they're getting this year in some way are related to the runs they got the last year, and a better result might take some of that into account. And again, it reminds us that correlation is not the same as causation. And if we're interested in a more causal relationship, we'd have to change the data we're using to create these estimates. So what the underlying estimation process is doing is it's basically very much as we did with our t-tests. We're assuming some level of normality of the standard error. So again, that our estimates, much like our estimates of our mean, or that there's for much the same reasons, the law of large numbers, and the other thing that we use is that we can basically assume that there is some level of normality of our estimates themselves. And so we get estimated standard errors for the coefficients. And this is what the estimated standard errors of the coefficients look like. Again, this is very much advanced material. This is just for those of you who are wondering where it's coming from. It's pretty interesting when you sort of pull this apart in a more advanced econometrics class. Part of it you would learn is you would learn the underlying math and how to derive these estimates yourself. It helps you make sense of more advanced math to have some sense of this. Again, not necessarily at this stage, but at some point as you get more advanced into methodological training, you might want to come back and revisit where some of these concepts come from. What's nice about these standard errors is it allows us to plot confidence intervals. And I can't remember if we have it in our assignment, but I can certainly show you how to do confidence intervals in your plot. So often you might want to present, if you've got some type of an estimated coefficient, you might want to actually put the confidence interval around it. It can be very useful, in some ways more useful for readers or audiences that you're presenting to. It might be more useful than a long list of coefficient results that they can't even begin to interpret. So every time we can visualize our data, one of the beauties of ours, it allows us to do that easily. But every time we can visualize results, it's often better to visualize them than to, again, give raw numerical results. So here again, we've got our t-values. So this is going to look very much like a regular t-test. We're in essence getting our estimates and we're taking the standard error of those estimates. So what we're basically doing, you can see from here, is much like a t-test. We're saying our estimate minus 0 divided by the standard error. Very much like the t-test we've done before. And again, using many of the same underlying mathematical principles to be able to do this more advanced regression using these t-test ideas. And going to do p-values. One thing I want to point this out is that what this means is that basically you can estimate a regression model without ever going on to then do this inferential statistics. So the line that you estimate is the line that you estimate, and it just simply describes the relationship. There are additional assumptions that then go into whether or not you can then make inferences about whether or not those numbers are statistically significant, i.e. different than 0. However, those aren't mandatory as part of the estimation itself, although the estimation does allow you to do this. And so finally, we would look at the probability of being wrong if we reject the null hypothesis. So this is our p-value. So again, if we basically say that there's not that there is not, let me see if I can get this right now. So the relationship between runs and salary is not equal to 0, i.e. there is an actual relationship. But if we reject that null hypothesis and say there isn't not a relationship, then we only have a 0.1% chance of being wrong. Because there's only a 0.1% chance that the number we observed could have been generated randomly if the true value was 0. Okay, that concludes this discussion. Again, there'll be a slightly more advanced section, but this is all of the mandatory lecture material for the second week of statistics in the course.